In this video, we'll talk about how to convert back and forth between standard coordinates for a vector and b coordinates for some basis b. In our last video, we saw the following. Let b be a basis for Rn consisting of vectors b1 through bn. If the vector x can be expressed as the linear combination c1 times b1 summed up through cn times bn, then we say that the b coordinate vector for x is the vector c1 through cn. Let's start by looking at an example. In this example, we have a basis b for R2 consisting of vectors b1 and b2, where b1 is 2, -3, and b2 is 5, -7. In part A of this example, we have the vector x equals 1, -2, and I want to find the b coordinate vector for x. So if I want to find the b coordinates for x, I would need to be able to write x as a linear combination of the basis vectors b1 and b2. So I want to solve the equation c1 times b1 plus c2 times b2 equals x for the weights c1 and c2. So this is the vector equation c1 times 2, -3 plus c2 times 5, -7 equals 1, -2. To solve this vector equation, I can set up the augmented matrix 2, 5, 1, -3, -7, -2. Then I can row reduce this to find my solution. Now I won't go through the details of row reducing here, but you should find that this row reduces to 1, 0, 3, 0, 1, -1. So my solution is c1 equals 3 and c2 equals -1, and those are my b coordinates. So the b coordinate for x is 3, -1. In part B of this example, we're given the b coordinates for a vector y. So the b coordinate vector for y is -4, 2, and we're asked to find the standard coordinates for y. So remember that the b coordinates for a vector are the weights used to write the vector as a linear combination of your basis vectors. So this tells me that y is equal to -4 times b1 plus 2 times b2. So that's -4 times the vector 2, -3 plus 2 times the vector 5, -7. So that gives me -8, 12 plus 10, -14, which is 2, -2. So 2, -2 are the standard coordinates for the vector y. One thing to note when we were calculating this is we did -4 times the vector 2, -3 plus 2 times the vector 5, -7. This here can be thought of as a matrix multiplication, so this can be rewritten as the matrix 2, 5, -3, -7 times the vector -4, 2. Looking at the matrix there, we see that it's the matrix containing the basis vectors as columns, right? We have b1 as the first column, b2 as the second column. And the vector that we're multiplying, that's the b coordinate vector for y. So again, to find the standard coordinates for y, we took the matrix containing the basis vectors as columns, and we multiplied it by the b coordinate vector for y. This matrix is what we call the change of coordinates matrix from b to the standard basis, and we usually call that matrix pb. From our example, we saw that if we want to convert from the b coordinates of a vector to the standard coordinates, we just have to multiply the b coordinate vector by the change of coordinates matrix. So we see here that the vector x is equal to pb times the b coordinate vector for x. Now if I take this equation and multiply both sides by the inverse of pb, then this gives us a way to calculate the b coordinate vector for x if I know the standard coordinates. So if I want to convert from x to the b coordinate vector for x, I just need to multiply by pb inverse. So let's look at a few more examples. So in this example, we have the basis b for R2 consisting of vectors b1 and b2, where b1 is 1, 2, and b2 is 3, -1. For part A, we're given the b coordinate vector for x, which is 2, -3, and we're asked to find the standard coordinates for x. So to find the standard coordinates for a vector, I would take the change of coordinates matrix pb and multiply it by the b coordinate vector. So remember that the change of coordinates matrix is just a matrix consisting of the basis vectors as columns. So in this example, pb is the matrix 1, 2, 3, -1. So x is the matrix 1, 2, 3, negative 1 times the vector 2, negative 3. So in this product, the top entry is 1 times 2 plus 3 times negative 3, and the bottom entry is 2 times 2 plus negative 1 times negative 3. So on top we have 2 minus 9, which is negative 7, and on the bottom we have 4 plus 3, which is positive 7. So the standard coordinates for x are negative 7, 7. In part B, we're given that the standard coordinates for x are 10, 6, and we want to find the b coordinate vector for x. So to find the b coordinate vector for x, we need to multiply PB inverse to x. So first, let's find PB inverse. Well, this is a 2 by 2 matrix, so I know that the inverse is 1 over the determinant times the matrix where we swap the diagonal entries and negate the off-diagonal entries. So in this case, we have negative 1, negative 3, negative 2, positive 1. The determinant for PB is 1 times negative 1 minus 3 times 2. So that's negative 1 minus 6, or negative 7. So PB inverse is 1 over negative 7 times negative 1, negative 3, negative 2, 1. So again, the b coordinate vector for x is PB inverse times x. So that's 1 over negative 7 times negative 1, negative 3, negative 2, 1 times the vector 10, 6. So this is equal to 1 over negative 7 times, in the top entry we have negative 1 times 10 plus negative 3 times 6, and in the bottom we have negative 2 times 10 plus 1 times 6. So that's 1 over negative 7 times negative 10 minus 18 gives me negative 28 on top, and on the bottom we have minus 20 plus 6, or negative 14. Multiplying by 1 over negative 7, we have the vector 4, 2. So this tells me that if x is the vector 10, 6, then the b coordinate vector for x is 4, 2, meaning x is 4 times b1 plus 2 times b2. Let's look at one last example. So here b is a basis for R3 with vectors b1, b2, b3, where b1 is the vector 0, 1, negative 2, b2 is 1, 0, 2, and b3 is 3, negative 2, 8. So in part A, we have that the b coordinate vector for x is 3, 2, 1, and we want to find the standard coordinates for x. So first I'm going to form the matrix PB, and that's just a matrix consisting of the basis vectors as columns. So the first column is 0, 1, negative 2, second column is 1, 0, 2, and the third column is 3, negative 2, 8. Next, to find the standard coordinates for x, I do PB times the b coordinate vector for x. So that's the matrix 0, 1, negative 2, 1, 0, 2, 3, negative 2, 8 times the vector 3, 2, 1. So in this product, the top entry is 0 times 3 plus 1 times 2 plus 3 times 1. The middle entry is 1 times 3 plus 0 times 2 plus negative 2 times 1. And then the bottom entry is negative 2 times 3 plus 2 times 2 plus 8 times 1. This simplifies to 5, 1, 6. So if the b coordinates for x are 3, 2, 1, then the standard coordinates for x are 5, 1, 6. In part B, we're given that the vector x is 2, 1, 0, and we're asked to find the b coordinate vector for x. So first we'll need to find PB inverse. To find the inverse of a 3 by 3 matrix, typically what you would do is you would make the augmented matrix PB augmented with the identity matrix and row reduce it. I won't go through the details of doing that here, but what you should find is that PB inverse in this problem is 2, negative 1, negative 1, negative 2, 3, 3 halves, 1, negative 1, negative 1 half. So to find the b coordinate vector for x, we do PB inverse times x. So that's 2, negative 1, negative 1, negative 2, 3, 3 halves, 1, negative 1, negative 1 half, times the vector 2, 1, 0. So for this product, in the top entry we have 2 times 2 plus negative 1 times 1 plus negative 1 times 0. In the middle entry, we have negative 2 times 2 plus 3 times 1 plus 3 halves times 0. And in the bottom entry, we have 1 times 2 plus negative 1 times 1 plus negative 1 half times 0. And this gives us the vector 3, negative 1, 1. So if x is the vector 2, 1, 0, then the b-coordinate vector for x is 3, negative 1, 1. So that's it for this video. In our next video, we'll talk about coordinate mapping, which allows us to think about any vector space as Rn.